Do you remember the first part of our video where we talked about derivation and origin of natural number? So now that we know all of the details, we would like to talk about the properties of this number, especially in the context of calculus.
But when it comes to calculus, we should bear in mind that we will talk about integrals and derivatives as well.
And of course, if we talk about the number e, we have to talk about the natural logarithm, which is just an inverse of exponential function.
And the natural logarithm is as mesmerizing as exponential function e in the power of x itself is. Well, what's happening? What are you looking at?
I mean, did you see the bicycle behind you?
Yeah, I can see it clearly, but it looks like you're craving for riding it.
Well, I think you're right. I'm quite keen on cycling, but
I have a challenge for you. Are you able to ride on this bicycle and simultaneously explain something about derivatives or calculus?
It doesn't sound like a challenge, but
you accept it.
Of course. Okay, let's try.
So let's try.
Well, did you ever wonder what is a derivative of a function? Well, you must have learned in school that in order to find a slope between 2 points, you have to divide the difference of y by the difference of x. But imagine you have a line that passes only through 1 point that lies on your curve. So in this case, you'll not be able to find the slope of the line because you know the pair of coordinates and you have only one such pair. So you have to do it differently, and there's an approach that was invented by Isaac Newton. He suggested that we find the slope of between 2 points, and with the condition that these 2 points are infinitely close to each other. So he wrote it in such a notation like the difference of y divided by the difference of x, and the limit when the difference of x becomes infinitely small, like when it approaches 0. And basically you can draw the tangent line at all points on your curve, and if you connect these lines you'll get a new curve, like a new function, and this function is called the derivative of your original function. So that's basically what the derivative actually is. It describes the rate of change of any function. So yeah, that's it. That's a derivative.
So we have given a short but clear explanation of what the derivative is, and now let's find the derivative of natural logarithm, which is written as ln.
So before talking about the derivative of the natural logarithm ln x, let's consider its graph and also the function, how it looks like, the curve of y equals ln of x.
Well, actually you can see that there's some distinct points on the graph. For example, there's a point 1, 0, so the ln of 1 is just 0. And also it's quite, it's clear that there's some problem at the origin, like the function is discontinuous here, so there's a vertical asymptote.
And I can notice that at the point of x equals e, the y value equals to 1, and it's quite reasonable because the base of ln is e, and e raised to the power of 1 is equal to the natural number e itself.
But I have a question, if we see the graph itself, can we actually derive any conclusions about its first derivative?
Looking at the graph, I may notice that at the point of the x value is increasing monotonously, I can notice that the value of derivative is also positive.
Yeah, because the function is always increasing. And
okay.
As I said before, there's the discontinuity at the origin, so I can assume that its first derivative will be undefined at x equals 0.
Yes.
Yeah. Anything else?
It's quite interesting because we can consider any function which is when the x value gets larger and larger, the graph itself is flattening out.
It's just slowing down.
If there is such a graph. Well,
so we have to find a graph that's always positive where it exists, which is undefined
at the origin, and also has a vertical asymptote.
And also it has to decrease over time with increasing x values. So we have to find such a function, or at least propose the one. Well, can you think of any?
It sounds like
what? You mean it's a hyperbola?
Yes.
Yeah, because it satisfies all the conditions. It's always decreasing.
It's quite reasonable to conclude that it's a hyperbola. Well, let's check it.
It's just an assumption, so we have to prove it.
Yes, to prove it.
Yeah, let's actually check it.
Now I will try to find the derivative of the function ln x, and in order to do this I will use the definition of derivative. So derivative is basically finding the slope between 2 points, but very close points. So let me write, just in case, the definition of derivative. So it's you subtract the values of the function that are close to each other, and you divide by the difference of the x values. So you subtract x plus h minus x, you'll get h, and you say that they are very, very close to each other. So that's the slope of the between 2 points, and that means that it's very close to each other. That's how we find the derivative. So let's apply this to the function ln x. So derivative of ln x will be ln x plus h minus ln x. I subtracted the y values and I divide by the difference of their x values, so that's h, and I say that they are very, very close to each other. Now I will use the properties of logarithm. I will use two properties. There are a bunch of different properties of logarithm. I will use two. First, I will say that when you subtract the logarithms, you can divide the things that are inside of logarithms. So instead of ln x plus h minus ln x, I will write ln x plus h over x, right? So I divided the things that are inside over h, I copied this, and I say that h approaches 0. Next, I will do the two things. First, let me write this h in front of the logarithm. So I will write 1 over h, right, ln, and inside I will divide separately x over x separately and h over x separately. I can do that. So x over x is 1, h over x is just h over x. Great. And the second property is that I can move the thing that is in front of logarithm to the inside, but to the power, right? So 1 over h will move inside, but as the power. So I will get h approaches 0, ln, no more 1 over h in front, 1 over h will be inside, ln 1 plus h over x, and this thing is in the power. Great. Whew. Final steps. Maybe this thing is familiar to you. This kind of limit, we got this kind of limit, like this part, the brackets and something in front, in the power. In our previous videos, something similar we've come across. So I will get there. So the final step is that, let me copy that, h approaches 0, ln 1 plus h over x. Now, I need in the power the same thing as here. So if it's h over x, it should be x over h, right? So there should be the same things but in the reverse. So if it's h over x, I need x over h. But if it's 1 over h, so I have to balance that. I cannot just add x to the formula, to the equation. So I balance it by dividing by x. So this whole thing, I guess, this whole thing will give you the number e. That's the number we've talking about, and we've derived this formula as well in our previous video. So that will give me ln, natural logarithm. This is e, just the number e, to the power of 1 over x. And finally, I did the reverse thing that I've done here, right? I moved 1 over h inside as a power. Now I will move this out from the logarithm. So I can move out the powers as I can move inside the powers. So that's, I can, since I eliminated h, I no longer can write ln, or limit. So I will get 1 over x in front and ln, yeah. And natural logarithm of e is just 1, so 1 over x. This proves that if you want to find the derivative of ln x, that's 1 over x.
And now, imagine we have...
1 minute.
No, not in this case.
Okay. Actually, it was in our previous part.
Yes,
so
it's too
kinda,
absolute to use it one more time.
So imagine we have an exponential function.
Exponential function that's
and
based on any value.
Any value, but because we're talking about the natural number,
Right.
let's use a range of bases between 2 and 3, so it would be like easier for us to compute it. And we'll try to find the derivatives.
That we take the number between 2 and 3 because you remember our natural number e and
It's 2.71. I
Yes.
hope you remember it.
we hope so.
Because it's really a memorable
Yes.
number indeed. So
Very
we'll,
necessary.
right. We'll try to find derivatives
Right.
of exponential functions.
Yes, and as you know, the derivative is the slope of tangent line.
Right.
Right.
And we'll use Excel for that.
Right.
Like in our left column.
As
we'll-
we constructed the table in our previous video, we'll use it one more time.
Right.
And in left column we would write base, right?
Right. Base.
Base.
Kind of base of an exponential point. You can just write a base.
Okay, and in the second column, let's write the derivative function.
In its standard notation, like f prime of x, as you know,
okay.
it's just a way to denote the derivative.
Okay.
And it's obviously the first derivative, we hope, because we have just one prime there. So, and we'll use the most basic exponential function, like, yeah, right, 2 to the x. It's a function that doubles itself with every additional x.
Right.
And to find the derivatives, we have, as you have said,
Calculator with us.
yeah, fortunately, a
Fortunately.
graphing one.
Yeah.
And I will write, as you can see, it's 2 raised to the power of x.
Okay. And
it
what
will-
does it equal to?
Okay, so it gave me the appearance of the function. Now I'll press sketch and choose a tangent line, but it will automatically show me this.
It's really beautiful sketch, indeed.
Right. Actually, yes, it is. But it's at x equals 0. But we need x equals.
X equals
Yeah,
1.
because it will be the most more easy to calculate.
Yes, right.
Just not to overcomplicate our matters.
This is
And
comprehensible.
Right, and as I can see, it's
1 point, okay.
1.3862.
6, 2. Okay. And
And-
let's increase our value, but we have a problem with our Excel, so I want to ask you one more time to repeat that.
Okay, it's 1.3862.
1.3862, right. So sorry for inconveniences one more time.
So we'll now
Let's
increase the
our
base.
value, our
And
base.
let's take like 2.1.
2.1.
Okay. So I will not calculate it for you. It's
2.
I'm just repeating the same steps and drawing the function, pressing sketch, the tangent, and at x equals 1, it's 1.558.
Okay.
And let's keep going. I mean,
2.2?
right.
Okay.
Okay. And it's
What is
1.7346.
Really amazing.
No, just you had 1 7. Like, remove it.
Is it odd?
Yep.
Okay.
And if you now continue doing so, I mean, let's say 2.3, it will be the
We
tangent.
increase our base every time
By
0.1.
0.1.
0.1,
Okay,
yes.
and it will be 1.9156.
Okay.
Um,
We can see that our derivative increases all the time
Which is
as
quite-
our base increases.
Yeah, which is quite a
and it's
logical thing because every time the function is growing
growing
faster at that point.
Yes.
Let's sketch it
2.4.
right, and it will be 2.1011.
Okay.
Repeating it, and
It has approached already 2.
okay, nice.
Okay.
For 2.5,
For 2.5.
it will be 2.2907. 29.2929. 07.
Okay.
And as you can see, we're just coming closer to the base of natural number.
Natural number, yeah.
Let's say it's 2.6. In this
Okay.
case, the derivative will be 2.4843.
2.43 and 2.7.
2.7, which is really close
It's
to
really
E.
too close. We're getting closer and closer every time.
Right. The derivative will be
Equal to
2.68. 2.6817. And Actually, it's
It's
quite
really
surprising that these two are really close. I mean,
close.
the base and
Yeah.
value of the
And
derivative.
it can tell us about something really
Oh, okay. Well, let's keep
interesting,
going.
but let's keep going and
yeah, one
find
more
out
time.
what's happening.
If it's actually coincidence or not.
Yeah.
Sketch tangent at 1. It's 2.88 to
2.88
to 9.
to 9.
And again, it's just going away from the value. And
It's really amazing that there's a great jump between 2.7 and 2.8.
yeah, but let's actually take something closer to the
Closer
e itself,
to the
like
E.
like 2.71. Okay,
Yes.
2.71, and I'm really excited to see what it would be. It's
Me too.
see, it's 2 points.
It's kind of scary.
Scary for me. No, no, like
Yes,
right.
it's really scary for me, but
No,
not in this case.
Okay. It's just a derivative. 2.7017.
2.701.
It's amazing.
It's really amazing. 2.71 and approximately 2.70, they are really too close to each other.
And let's go further, like 2.722, maybe.
72, yes.
Actually, if you remember, as we have said before, e is 2.718, so it's approximately 2.72. So it's really close to
Close
e.
to E.
And let's see what it will give me. It's
Really?
2 point. You will not believe me, but it's 2.7217.
7217, really?
Whoa.
Wow, what is it?
But let's actually try the e itself,
Yeah.
because my calculator can do this. Just watch it.
I'm too excited to do it.
Just write an e. Okay. And I will insert it here.
Oh my god.
Draw and sketch the tangent at
Okay.
what? It's 2.7182. 2.7182.
Really?
Yep. And
What?
just a minute, does it actually mean that the derivative of e is e
Is it? It's equal to E, really?
to itself? Like, I've never seen any.
It's too mind blowing.
Right. I've actually never seen a function whose derivative is the same as the function itself.
Yeah.
It's really surprising because we have actually tried
Yeah.
other bases and it didn't work out, but
Another
exactly with
application
this
to
one,
make such
it's
situation.
really surprising.
It's really amazing and surprising, yeah.
Okay, it's mind blown. It's kind of mental breakdown.
Science creates magic, but mathematics,
Yeah, it's,
yeah, you know,
I'm
it's
shocked.
full of mysteries.
wow.
Wow.
So now that we have seen that the derivative of exponential function with the base of natural number is equal to the function itself, I can make quite a logical conclusion by writing that the integral, which is an antiderivative, like the integral of e raised to the power of oops, no worries.
Sorry, I apologize.
No worries.
Oh,
So,
sorry.
yeah, I was trying to find the integral.
Oh, it's integral of it.
Yeah, of the
okay.
exponential function.
I'm familiar with
That
this function. Okay.
so from the negative in infinity to 1.
1. Okay.
So when it will be equal to.
But how can you plug the negative infinity in this case?
Yeah, actually that's quite a reasonable concern. Let me change it. Let me write it as a.
A.
And actually I'm just changing the notation. A approaches the negative infinity. So do you agree that it's the same thing?
Yeah, I agree with you.
So then in this case it will be the limit
Limit.
as a approaches negative infinity. Antiderivative of e to the x, like the function
It's
itself.
it's the same function, e to the
Yep.
power of x.
So from to 1,
Okay.
1 a, it's it will be equal to e raised to the power of
the
1
power of
minus the limit e raised to the power of like I'm plugging it. Okay, I should write it like more accurately,
It was quite strange.
like that.
Okay.
Minus limit. I'm just plugging a here. A,
A.
if it looks like a. Yeah. And a approaches negative infinity.
It looks like
Excuse me.
8,
Yep,
but
it does.
let's write it. Yeah, more in the shape of it.
Okay.
Okay.
So this will be just like the e.
E itself.
And here I'm plugging some infinitely large numbers with like to its as its power, so it will approach 0.
0.
So minus 0
is equal to e.
e.
Okay.
And do you notice something interesting
Yes,
about it?
the integral of e to the power x is e itself.
Yeah, and
the
also
derivative of e
yeah, like the
is
slope
e
of the tangent
itself.
line
Yes,
is also
okay.
the function stuff, and also the value of the function at 1
One
is also like
one.
e.
Yes, it's
So
quite amazing.
yeah,
Yes,
but
perfect.
yeah,
Yes,
it's really
wow.
amazing that
Amazing.
there's such a function
Yeah,
with
yes.
all of the three
Of
properties
course,
having the
yes,
same value.
Well, as Mr. Elnur has demonstrated us earlier, the derivative of ln, which is natural logarithm, is equal to 1 over x. And in this part, we would like to turn to integrals. As you know, integral is another term for antiderivative, and if we use integrals, I would like to write the following formula. The integral of 1 over x, we should bear in mind that we should write dx in this case, is equal to ln x plus c, and I would like to explain that we write ln x because, as Mr. Elnur has showed us, the derivative of ln x is 1 over x, and we should write
Hey, what
c
are you doing?
Yeah.
You're trying to find
The integral of hyperbolic
okay, that's
curve.
but I have a question. Like, if you rewrite a hyperbola as x to the power of negative 1,
By the conventional power
yeah, by the
rule.
conventional power rule,
Okay.
like, what will happen if you use
Okay.
it?
According to the power rule, x in the power of n, if we find its derivative,
Yes.
the n comes as a coefficient before x, and we multiply it by x, and the power of n decreased by
Okay,
1.
yes, that's
N minus
quite
1.
obvious.
And 1 over x is x in the power of negative 1. And if I equal x in the power of negative 1 to x in the power of n minus 1, it turns out that n minus 1 is equal to
So n is
negative 1.
0.
N is 0,
Yeah,
right.
okay.
And if I write it as an integral, the integral of, if I write this term, I
But
don't
you're
use
just-
n because we find that n is 0, and if we multiply any value by 0, it doesn't make sense.
Yeah.
And the right integral of x in the power of n minus 1 dx, it is equal to
X to the power of n.
in the power of n
But-
divided by
oh, yeah.
n.
And n is
And
0.
If I substitute 0,
Yeah, and you're dividing by-
it's
okay.
x in the power of 0 by 0.
So it's just 1 over
Yes,
0.
1 over 0. Any value in the power of 0 is equal to 1. And 1 over 0 does not
Okay,
make any
so-
sense because we find 0
Yeah, I
and
see the
then
problem, but
Okay.
don't you think that's truly amazing that it's just a
Yes,
conventional
it was.
hyperbolic curve, but
Yes,
when you
yes.
try to find the area, you use a natural number in the form of log.
Yes.
Like, it's really interesting.
So what we're going to do now is to find the area under this function. This is the function of 1 over x, as you know. So in order to approximate, we will not be able now to find the exact area. In order to approximate the area under this curve, we'll use the technique that Riemann used. And the technique is that he divides the area under the curve into figures, and maybe you'll guess what the figure is.
Rectangle?
Okay, rectangles, there are a bunch of different figures as well, different techniques, but rectangle are more efficient for any other reasons. But now we're gonna divide, so our interval is from 1 to e. We're gonna divide this, for now, let's divide it into 4 subintervals, okay, 4 rectangles. So the first interval will be here, then here, then here, and then here. So let me grab the ruler. So the first one is here, and by the way, this is called the left Riemann.
So it's because you are taking like the left value from each interval, right?
Yeah. So from this interval, I will take the left x value, and I'll take the y value of this of that function. So here I will take from this interval, I will take this. From this interval, I will take this, and from the last interval, I will take this. Now, what I do next, I will just complete the rectangle, right? So that's somehow will be my first rectangle. Now it's gonna be the second rectangle. That's gonna be the third rectangle, okay?
And finally,
okay. So now we can assume that the area under the curve the area under the curve, under the black curve, is approximately equal to the sum of the areas of these four rectangles. Now, yeah.
Well, yeah, but considering like these pieces, for example, this one, I can assume that it will be greater than the real value of the area.
Exactly.
Overestimation.
Our approximation is overestimation because we considered the things, the parts that we don't need for now. But
But are there any ways to do more precise approximation?
What Riemann thought about is, let's divide it into 8 intervals. Now let's a little bit increase the number of rectangles and see what we'll get. So don't repeat it at home because it's dangerous. Now we have 8 rectangles. Come a little bit closer. So we have 8 rectangles, 1, 2, 3, 4, 5, 6, 7, 8. And as you can see now, the parts that are overestimate the area are less than they were before, right? So we can we can assume that if we increase the number of rectangles more, like it will take 16 rectangles, 32 rectangles, I don't know, 64, and then more and more and more, we'll be closer to the real area under the curve. We can now repeat it like on the paper because it's going to be more and more rectangles. So for this, I'm going to use Python. As I said, I will try to find the area under the curve 1 over x from 1 until e using Python. So let's dive in. First, I will import the math because my computer doesn't understand what the number e is. It doesn't understand the number e equals to 2.718 and so on. And I will import that information from the library called math. And let's define the starting position. So I want the program to start from x equals 1 and end with the number e. And the way I tell the program that I'm talking that number e is math.e. That way it will understand that I'm not talking about just the letter e, but the number e that is equal to 2.718 and so on. After that, I will need the number of rectangles. And I will ask the user to input the number of rectangles. And I will print the message, please input the number of rectangles. Great. So after that, after the user inputs the number of rectangles, I will want to find the width of each rectangle. So let's say that this is the function 1 over x, right? I drew the 3 rectangles for now, just 3 rectangles. And we will need to find the area of each rectangle. In order to find the area of each rectangle, I will need the width of each rectangle. So it starts from 1 and ends with 1.6. You know the starting position and you know the end position. So 1 and 1.6. How can we find the width of each rectangle? So in order to find the width of each rectangle, I will subtract 1 from 1.6, and that way I will find the whole length of this interval, right? And then I will divide it by 3 rectangles, because now I have 3 rectangles. That way I will find, so 1.6 minus 1, it will be 0.6. 0.6 is whole this length, and I will divide it by 3. So I will find 0.2. So what the logic is, from end, I will subtract the start and then divide by the number of rectangles. So let's write that down. So the width is subtract start from end and divide by end. That's how I find the width. And after that, I have to define the function that will find the area. So let's call it area finder. I'm gonna pass 2 variables, x, the x value that I'm currently in, and the width of each rectangle. So what I want the function to do with these 2 information, first, it has to find the area. How to find the area? Let's find out the logic of how can I find the area. In order to find the area of this rectangle, let's say, I have to multiply the length or the height by the width, right? So I have to multiply. So I'm gonna tell return return, so length, right, times width. Great. So let's find out what is the length, what is the height of the rectangle, what does the height mean? So height is just the y value of my function, right? It's 1 over x, and this is just the y value of this x value. So it's 1 over x. If I want to find this length, I will need to substitute 1 instead of x in my function. So my function is 1 over x. I will substitute 1 instead of x. 1 over 1, I will get 1. That's why it's 1. In order to find the height of this rectangle, I will need to substitute 1.2 instead of x in my function, right? So it's going to be 1 over 1.2, something like that. So in order to find this height, I will need to substitute 1.4 instead of my function, instead of x in my function. So it's going to be 1 over 1.4 and so on. Why 1 over 4? Because my function is 1 over x, 1 over whatever I'm in. So the length is 1 over x, and the width is just the width, right? So multiply that by width. And that way I will find the area of the rectangle and return that area to me. So what else? I think we have to define the, at the beginning, the x is just the start. So x is 1. And I'm gonna start the process. While x is less than or equal to the end, so I'm telling the program, until you reach the end, do this. Do what? Find the area. So find the area with the variables x and width, okay? And I have to tell the function not just to find the area, but add that area to my previous areas. So let the previous areas be stored in the variable called total area. At the start, it's 0. And after you find the area, I'm telling the program total area equals total area add new area. So that line, what does that line do is it finds the area of the rectangle and adds to the previous area, and that will be equal my new area. And after that, I want to tell the program to move forward, not just to find the area of one rectangle, but after you find the rectangle, you add it to the total area, find the next one. And how I'm going to tell the program to find the next one, to move forward, I'm going to tell that now my new x is the old x plus the width. So after it found the area of this rectangle, it will add to x value the width. So it's 1.0.2 in this case, in this picture, in this graph. So it will move to this x next time, and it will find the area of this rectangle. Then add new width. After you find the area of this rectangle, add the width again and move forward. Now find this area, and every time it will find the area, add to the total area, and then move forward. So that's what this does. And after you complete that, and by the way, continue these 2 steps until you reach the end, until my x value is the number e. Continue this. When you reach the number e, stop it. And after you stop, print total area. Let's run the program, and I hope it will work. And now let's first have 100 rectangles. With 100 rectangles, the area under the curve is 1.011. It's pretty close to 1, and I can say that it's approximately 1. Okay, let's now have not 100, but 100,000, right? It's 100. Is it 100,000? It's 100,000. Great. Okay, it's 1.5 zeros, 543, and so on. I think it's great. Now let's have a million rectangles, right? A million rectangles. That's huge. oh, it's 1.6011. It's so close to 1 that I can say it's 1. And you see that every time it becomes closer and closer to 1. But let's not stop here, and let's have a billion rectangles. Billion rectangles is 1 with the 9 zeros. All right, and let's start. Oh, as it turns out, my computer is not strong enough to calculate it immediately. So keep in mind what I do. I'm not increasing the range. I'm not increasing the interval. Interval stays the same. Interval is from 1 to E. It's always the same, from 1 to E. What I increase is the number of rectangles that are inside that interval. So in my first example, it was 100 rectangles. So I found the area of 100 rectangles from 1 to till the number E that are fit inside that interval, 100 rectangles. Then I increased to 100,000, then I increased to 1 million rectangles. Can you imagine 1 million rectangles inside this interval, inside the 1 to E? That's huge. Now I'm telling the program, calculate the areas of billion rectangles from x equals to 1 to x equals to 2.718 and so on. And I hope that it will give me the number, but we will have to wait. So let's wait.
Three weeks later.
It found, so it's 1 point, I guess it's 7 zeros, 7, let me find it out, 1, 2, 3, 4, 5, 6, 7 zeros, and then 12, 90, 0, 5, 5, 1, so it's pretty close to 1. If we continue increasing the number, like if I had a stronger computer, we could have increased the number of rectangles to, I don't know, to several billions, and it will become more and more close to 1. So that's it.